Hello everyone, welcome to the sixth session on semiconductor fundamentals. In this session, I will be discussing on light emitting diodes. The LED has displaced traditional incandescent or filament based light sources in many applications due to its high efficiency in turning an electrical energy input into a light output. They are small, physically robust, operate relatively cool, and are available in a number of different colors. The schematic symbol of the LED is shown in figure 1 here. The basic idea behind its operation is fairly simple. In a forward biased PN junction, when free electrons recombine and fall into lower energy valence holes, they must give up this energy differential in some manner. In most diodes, this energy is emitted as heat. In LEDs, however, the energy transition is designed such that it is radiated at shorter wavelengths, that is, visible light. In order to achieve this, LEDs are not formed just by using silicon as in a typical switching diode. Instead, somewhat more exotic materials are used. From an analysis or design standpoint, the important thing to remember is that the forward voltage drop tends to be noticeably higher than that of the silicon, which is 0.7 volt. The precise value of this voltage drop will depend upon the material, which in turn affects the color of the light itself. A generic red LED will likely exhibit a forward voltage drop of around 1.8 volts or so. Other colors tend to be somewhat higher as we move through the rainbow, ending with blue and ultraviolet LEDs, and also high brightness versions up to around 3 to 4 volts. In a lab, it is easy to determine the approximate forward voltage of a given diode by connecting it in series with a voltage source and current limiting resistor. The supply is increased until the desired brightness is achieved, and then the diode drop can be measured with the help of a digital multimeter. When reverse biased, the LED behaves like a switching diode, that is, it looks like an open switch. Unlike switching and rectifying diodes, LEDs' maximum reverse potentials tend to be relatively low, perhaps just a few volts. With a brief introduction to the LEDs, now let us go and understand the working principle of the LEDs in much more detail. A light emitting diode is a two LED semiconductor light source. It is a PN junction diode that emits light when activated. When a suitable voltage is applied to the leads, these are the two leads here, positive and negative here, to the leads, electrons are able to recombine with holes within the device, releasing energy in the form of photons. This effect is called electroluminescence, and the color of the light corresponding to the energy of the photon is determined by the energy band gap of the semiconductor. The material used in LEDs is basically aluminum gallium arsenide. In its original state, the atoms of this material are strongly bonded. Without free electrons, conduction of electricity becomes impossible here. By adding an impurity, which is known as doping, extra atoms are introduced, effectively disturbing the balance of the material. These impurities, in the form of additional atoms, are able either to provide free electrons, which are of n type, into the system, or suck out some of the already existing electrons from the atoms, for example p type, creating holes in the atomic orbits. In both ways, the material is rendered more conductive. Thus, in the influence of an electric current in n type material, the electrons are able to travel from anode to cathode and vice versa in the p type of material. Due to the virtue of the semiconductor property, current will never travel in opposite direction in the respective case. From the above explanation, it's clear that the intensity of light emitted from a source, LED in this particular case, will depend on the energy level of the emitted photons, which in turn will depend on the energy released by the electrons jumping in between the atomic orbits of the semiconductor material. We know that to make an electron shoot from lower orbital to a higher orbital, its energy level is required to be lifted. Conversely, if the electrons are made to fall from the higher to the lower orbitals, logically energy should be released in the process. In LEDs, the above phenomenon is well exploited. In response to the p type of doping, electrons in LEDs move by falling from the higher orbital to the lower ones, releasing energy in the form of photons or light. The farther these orbitals are apart from each other, the greater the intensity of the emitted light. Different wavelengths involved in the process determine the different colors produced by the LEDs. Hence, light emitted by the device depends on the type of the semiconductor material used. Infrared light is produced by using gallium arsenide as a semiconductor, and we have a few examples given here, and you can understand what are the compositions of an LED to create a certain certain color of light. For example, as I already said, infrared is obtained by gallium arsenide. Then we have red to infrared or orange, gallium arsenide phosphide. To get a very high brightness red, orange, orange red, or orange and yellow, we have aluminum gallium arsenide phosphide. So you can look at this slide and probably you can note down what are the different possible combinations you need to create in order to obtain a certain color of light from an LED. There are in fact different types of light, as we are looking at this slide here, that are available in the market, and there are different LED characteristics which include the color, light or wavelength radiation as well as light intensity. The important characteristics of the LED is obviously the color. In the starting use of LED, there is only the red color. As the use of LED has increased, with the help of the semiconductor process and doing the research on the new metals for LED, the different colors were formed. And now you're looking at the VA characteristics of the LED with different colors which are indicated by the characteristic curves. As per the color of the light that is emitted, the characteristic curve would either shift left or right. So if I take the colors of the rainbow, which in fact is usually VIBGAIA, as I start from the violet towards the red, the characteristic curve moves towards the left. So here we have the x-axis as the forward applied voltage and the y-axis is the current across the diode itself. Now we come to the advantages of the LEDs. Very low voltage and current are sufficient enough to drive the LED. The voltage range would be somewhat around 1 to 2 volt and the current range would be around 5 to 20 milliamperes. The total power output will also be pretty less, which is around 150 milliwatts. The response time is also very less, only about 10 nanoseconds. The device does not need any heating and warm-up time and is therefore quite fast. It is miniature in size and hence can also be very lightweight. It is very rugged in particularly construction and hence can withstand shock as well as vibrations. Lastly, an LED has a lifespan of more than 20 years, which is considerably higher, in fact significantly higher than the old generation incandescent bulbs. However, they have a set of disadvantages as well. A slight excess of voltage or current can damage the device. The device is known to have a much wider bandwidth compared to the laser diodes. The temperature depends on the radiant output power as well as the wavelength. Well, we have now come to the end of this session. To summarize, we have discussed in this session about a brief introduction, working principle, VA characteristics, LED combinations for generating different color lights as well. I hope you found this session informative. Thank you for watching. Have a good day.